Welcome back. In this video series, I will explain how to create the simulations of vortex-induced vibrations of a cylindrical structure in OpenFOAM. And in the previous videos, I explained how to create the geometry in Salome and export as an STL file. And we also created the mesh using block mesh and snappy hex mesh. Now we have the OpenFOAM mesh, which we can use for a simulation. But for the next step, we need to assign the boundary conditions, the physical properties of the fluids, and numerical schemes. And also we need to choose the right solvers. Okay. In this video, I will explain the boundary conditions to be used in this simulation. So let's go ahead and look at it. So this is the boundary conditions of our domain, and we have the inlet with constant velocity and the x direction, and we have all the side walls where you can assume these as slip walls. We can call it slip walls, where there is no flow out perpendicular to the outside of the boundary. The flow can go just parallel to the wall, but not perpendicular to the wall. Okay, and we can have the pressure zero gradient boundary condition for the pressure. Okay, and for the standard for the outlet, we have zero gradient boundary conditions for the velocity and zero pressure for pressure. Okay, and for our cylinder, we wanted to move in the cross flow direction, so the boundary condition should include this motion effect. So such boundary condition is called moving wall velocity. So let's look at this table, and here for the inlet, we assign something called fixed value boundary conditions for velocity, and this 1 0 0 is the vector. It means x, y, z direction. So we assign the x velocity to be 1 meter per second. And for the pressure, this is the keyword required for the zero gradient boundary condition. And for the outlet, we have zero gradient for velocity, and for pressure, we have fixed value. Okay, uniform zero boundary condition, and so it basically means the pressure here is zero. And for the sides, we can use symmetry boundary conditions, and for the top we can use slip wall. So the symmetry and slip wall boundary conditions are basically in terms of numerical calculations, it's the same. We can use them interchangeably, and I can change here right now, but in OpenFOAM there's some it's said that some difference in numerical implementation, and we can see a small difference between these two boundary conditions in ParaView. It's most about the visualization problem, but anyway, we can use these two interchangeably. Both of these mean we have no velocity outside perpendicular outside or inside, coming out of or coming inside into the boundary, and in the flow parallel to the wall, we don't care. This is just slip. Okay, and for the bottom, the original paper uses symmetry boundary conditions, but I chose the non-slip wall. Anyway, it will make not so much difference because we have a huge gap between the bottom and our structure. Anyway, if we want to change this to slip walls or symmetry, it's easy, and we can just change it. Okay, the most important is the cylinder. We need to assign a moving wall velocity boundary condition, which means, as I said before, it will take into account the motion of the cylinder to spread the velocity field. And for the pressure boundary condition, of course, we have zero gradients. Okay, so let's go ahead and actually see the boundary conditions. So we have our zero directory here, and in this zero directory we have u and p. U means velocity and p is pressure. Actually, we can have several files, and most of these are for turbulence boundary conditions, and this one is for mesh motion. So I will not touch about these for now. So I'll only look at the velocity and pressure boundary conditions. So this is u, this is velocity, and this is the dimensions. So we can see that this comes like kilogram meters per second. So it means a velocity is in meters per second. We can I need to comment out. We can check here whether our boundary condition, whether our file is good or not by checking the dimensions. And for the internal field, it means okay, this whole domain as an initial condition, it will be 0, so there will be no velocity at the very start. And for the sides, we can see the symmetry. And for the inlets, this is how we set the 1 meter per second in x direction. Type is fixed value, and value is uniform, and we can write the vector inside the curly brackets. And for the outlet, we can use type as zero gradient and bottom type as non-slip. So basically we have the name, and we have two curly brackets, and inside the curly brackets we can have the boundary conditions. And first there comes the type, so it is a must, and if it's fixed value, we need to provide the value. So this is the velocity vector field, so we provide the vector quantity. Okay. For the top, it's slip. For slip and non-slip walls, we can write like this, or we can, for non-slip walls, we can use fixed value like this. So we can give the fixed value, and the velocity is 0. So these are interchangeable. We can use any one of these. Okay. And for our cylinder, we need to define our motion, and we need to define moving wall velocity, and the value should be uniform 0. It means we assign a non-slip boundary condition even if the wall is moving. Okay, so it means the velocity closest to the wall is the same as the motion. It's the same as the velocity of the wall itself. It means the velocity of the cylinder itself. So what if I write like this? So it will artificially add another 1 meter per second to our cylinder, so it's not good. For most of the time, especially for using dynamic meshes with moving parts, this is a typical definition of our velocity boundary conditions. This is very important for, especially for dynamic meshes. But again, if we want to assign some moving walls like almost slip walls, we can assign the velocity here. Okay. For the pressure, you can see now the object is P, and we can see the dimensions. Now we have a strange thing. We have kilograms, meters, and seconds. So the pressure is here. It's meter squares per second square. So it's like this. So why it isn't in Pascal or like kilogram meter per second square? Sorry, kilogram meters per second, kilogram per meter per second. Okay, anyway, why isn't in Pascal? Why there is no kilogram here? So because I use pimple form. These OpenFOAM has incompressible solver family, and this whole family is like they don't care about the density of the fluid. The density is already and always constant, and so we don't care about the density term, and everything is divided by the density. So actually this pressure is already divided by density. It's not like a pressure, it's pressure by density. Okay. And for the boundary types, we can see inlet is zero gradient and outlet is fixed value with uniform 0. So now this is scalar quantity, so there is no vectors, so you can just assign like uniform 0. So if the pressure is non-zero, we can assign here, but this is fundamentally we always assign 0 pressure at the outlet, and it's a 0 gradient for the inlet. Okay. For the other parts, we can have 0 gradients, and for the sides, we need to type symmetry. The only thing we need to care about the symmetry is when we define some boundary condition to be symmetry, we need to write symmetry for everywhere, like for both velocity and pressure. And even if we have turbulence boundary conditions like k, omega, epsilon, we need to define symmetry for the sides. Okay, that's it for now. Thank you very much.